Hello, I am David W. Parker. This is Programming Today. I Learned 3D Math Series Episode 20. We're going to be looking at more matrix math, and we're going to be computing a determinant of a matrix again. This time we're going to be doing it in an n by n matrix. So let's go ahead. We have to define a few things in order to get started. So just to recall, the determinant of the matrix is equal to the triple product of three vectors, if you're assuming that each of the three rows of a 3 by 3 is a vector. So you have the determinant here of ax, ayz through cz here, and then this is the equation derived in the last episode, and you can see it's equal to the quote triple product of the a cross b dot c down below. Another useful thing that we're going to need to know is we're going to need to know what a minor of M is, which is a minor of a matrix. The submatrix M of ij is derived by deleting row I and column j from matrix M. Well, what does that look like? It's very simple. So suppose we have the minor of M21. We're going to delete the second row, so where it says -2, 1, 1. In the first column, 3, -2, 1. We're going to have a new matrix here, which is just the last two elements of the top row and the bottom last two elements of the bottom row, because everything else has been deleted. So we have 4, 2, 3, 2 remaining. A cofactor of a matrix is the sign determinant of the corresponding minor of M. So C of ij is equal to -1 to the power I plus j times the determinant of M of ij. So that seems like a little confusing at first, but we'll get into it and know how it's not that confusing. The minor is a matrix quantity. The cofactor is a scalar quantity, meaning it's just there'll be some kind of whole number. The term I of -1 to the I plus j is basically just showing that every single computation is going to end up being plus or minus. So it'll just be go plus, minus, plus, minus, plus, minus, and so on and so forth when you are looking at it in a checkerboard way. Well, now we're going to be able to use those to compute the matrix of an arbitrary dimension n. In terms of its cofactors, we're going to select a row or column. It could be any one that we want. For each element in that, we're going to multiply that element by its cofactor. Summing these products yields a determinant. So this is, and it's recursive. So here's the determinant of M is equal to the sum of the elements in there, where it's the matrix element times the cofactor. This is the cofactor over here expanded out. So you can see here we have the recursive nature of, we haven't yet another determinant. So what does this look like in practice? If we're going to do a 4x4, here's the 4x4 matrix up top. We're going to basically take the top row, and we're going to go ahead and say here's the element M11, and since we're doing the minor, it's going to be multiplied by the minor here. We're going to have 2, 2, basically everything that's not in the top row and top in this first column, minus, because it's plus, minus, plus, minus. We'll take the second element here, M1, 2, and the remaining, we'll take out the entire top row and then the second column, and then have the minor over here, so M21, M23, M24, so forth, so everything outside of the second column and first row, plus the third element, M13, times the minor here of everything that doesn't include the third column and the top row, minus the last one here. So, and obviously with each of these minors, it's recursive, so you're going to need to determine the cofactor of each of these 3x3s and basically expand this out respectively. So as you end up having more, 5x5, 6x6, it obviously involves a lot more recursion, and it's a lot of work to do it by hand. I'm going to leave it up to you in order to check out the fact that each of these ends up being expanded out. If you, I believe this is called the Laplace determinant equation, I believe. I did not write it down, but I will make sure to put that in the show notes. Characteristics of determinants that you should know. Determinant of a matrix product is equal to the product of the determinants. So determinant of A multiplied by B is equal to the determinant of A times the determinant of B. And this expands out to as many matrices as there is. So it's not just 2. Determinant of a transpose of a matrix is equal to the original determinant. So determinant of M of t is equal to determinant of M. Last few things to know: if any row or column is all zeros, the determinant of the matrix is 0. Exchanging any rows or pairs of columns negates the determinant. And adding any non-zero multiple of a row or column to another row or column does not change the value of the determinant. So that's it for this episode. That's it for determinants. If you like what you saw today, go ahead and subscribe and give me a like. Share it on social media if you will. And go to ProgrammingTIL.com and sign up for a newsletter. Have a great one.